In this episode, we are going to perform a chi-squared hypotheses test. In a chi-squared hypotheses test, we have bivariant data, meaning we're talking about two different variables. So let's take a minute and read the prompt. The Titanic sank in the early morning hours of April 15, 1912, in the North Atlantic Ocean, 4 days into her maiden voyage from Southampton, UK to New York City, United States. Below is a table illustrating the survival outcomes of individuals from the Titanic disaster, categorized by their status as crew members or passengers in first, second, or third class accommodations. Do the data provide convincing statistical evidence of an association between survival rate and status on the ship? Test an appropriate hypothesis and state your conclusion. We know when we're dealing with a chi-square test, we need to write out both our null and alternative hypotheses. In this case, we have a chi-squared test for independence. So the null is always that it doesn't matter where you were staying on the ship. It doesn't matter if you were crew or if you were first class, second class, or third class. It doesn't matter. Your survival rate is the same for all of those peoples. And the alternative is no, that's not true. There appears to be an association between status on the ship and survival rate. So take a second and please write down the null and alternative hypotheses. The null, survival was independent of status on the ship, which means it doesn't matter, right? They're independent. One does not affect the other. And the alternative is there appears to be an association between survival rate and status on the ship. Step 2 in our hypotheses test is always check the conditions. And there are two conditions that we are aware of for the chi-squared test. It is the randomness condition and the expected counts condition. So first, the randomness condition. Because this is a census, that means this is about everybody on the ship. We have all the data. Because it's a census, we do not need to check for randomness. Because remember the goal of randomization. The goal of randomization is that we randomize so that we can take a sample that's representative of the entire population. In this prompt, we have the entire population. So we do not need to check for randomness. The second condition is the expected counts have to be greater than or equal to 5. Well, how do we find our expected counts? Let's go to our graphing calculator. The first thing we need to do is we need to put this table into our graphing calculator. So we are going to go to second, and then see right above the x to the -1, it says matrix, second matrix. This is where we're going to put our table. We're going to arrow over to edit. And we are going to enter a 2 by 4 table. So 2 is the number of rows, 4 is the number of columns. And you see here, I entered all my Titanic data. So just take a minute and enter that data into your calculator. Once you do that, we're going to hit Stat, arrow over to Test, arrow up to chi-squared test. And again, this is a chi-squared test because we have bivariant data. We're talking about two different variables, survival rate and where you were staying on the ship. Were you first class, second class? Did you stay with the crew? Those are the two variables of study. It says, are you observed in list A? Yes, they are. It is going to put your expected in list B. And if you arrow down, it's going to calculate all the information we need. And we'll go back to this in just a minute. I just wanted to show you how to find your expected values. So we're going to go back to second, matrix, arrow down to B. And if you hit enter twice, you see here your expected values. So this first column is for crew. We expected 285.48 crew members to survive, and we expected 599.52 to perish. And how do you see the rest of these numbers? You just arrow to the right, and you can see all of your expected values. And here's the list of expected values for this data set. And remember, we need both the observed values, which are in the original table, and the expected values in order to show our work as part of the mechanics. In addition, we have to say that our smallest expected value, which is 91.94, it should say here that 91.94 is greater than 5. Okay, so you always have to use context of this problem. Our smallest expected value is 91.94, so you would say 91.94 is greater than 5. Moving on to step 3, which is our mechanics. And again, you're going to need to look at your original table and our expected values. Please take out your AP formula sheet and locate the equation for your chi-squared statistic. Again, this funky x with the exponent 2 is our variable for chi-squared. It says chi-squared equals the sum of observed minus expected squared divided by the expected values. So we're going to plug into that formula. And again, we just need to show that we understand how to plug into this formula to get full credit. So I used the first observed value, which is right up here in the table, 212. I subtracted from it the first expected value, 285.48. I squared it and I divided it by the expected value. And then I used the very last corner. Okay, so I showed the first, and then I showed the last, observed minus expected squared, divided by expected. And that's what you see in this formula right here. And again, let's just go back to our calculator, because our calculator will give us the rest of the information. Stat, arrow over to tests, up to chi-squared test. Our observed are in A. We saw our expected in B. And here we get our very large chi-squared statistic of 187.79. And we get a p-value of 1.829 times 10 to the negative 40, which is so small, it's approximately 0, right? Degrees of freedom. How do you find degrees of freedom in a chi-squared test? It's rows minus 1 times columns minus 1. And in this case, we had 2 rows and we had 4 columns. 2 minus 1 is 1. 4 minus 1 is 3. 1 times 3 is 3. That's where the degrees of freedom came from. And take a minute to make sure you have all the information you would need to receive full credit on the mechanics part of the hypotheses test for chi-squared. And finally, we need to state our conclusion. And just a reminder, with a very small p-value, we know we're going to reject our null hypotheses. And there's strong evidence of the alternative. So here, we would say with a p-value of approximately 0, much smaller than an alpha of 0.05, we reject the null hypotheses. There is statistically significant evidence of an association between survival rate and status on the ship. First-class passengers had the highest survival rate at 62%. The chances of survival increased with social class, as measured by the class in which the passengers traveled. which means first class passengers were most likely to survive. Second class passengers were then in second of survival, third class passengers, and then finally the crew. Um, and again, where did I get the 62%? If you look back in the original table, 202 out of 325 is the percent of first class passengers who survived. So 202 divided by 325 is roughly 62%. As opposed to, if you looked at all the people who survived on this ship, 710 survived out of 2,201, which is basically a survival rate of 32.3%. In addition, we know that the chi-squared component, this little piece, remember the chi-squared statistic is made up of all these little components, these little pieces that are added together are called chi-squared components. The chi-squared component for first class passengers was the largest component, which led to a high chi-squared statistic. A high chi-squared statistic leads to a small p-value. And one last thing I want to point out, again, if you go to stat, arrow over to test, up to chi-squared test, if you go to draw instead of calculate, you'll notice the chi-squared curve, unlike the normal model, is not symmetric. It is always a right-tailed curve. Okay, so just a reminder, the chi-squared curve is not symmetric, and a high chi-squared value always leads to a small p-value. That's it for this episode of Miss Mac's Academy.